moving forward with our network layer module, and today we'll start with quite a complex topic, and we'll talk about routing. We'll start with the routing algorithms and then switch to routing protocols. And the first routing algorithm that we're going to be talking about is a link state. But before we're going forward, let me just brief sidestep. So why do we need routing algorithm or protocols or whatever? So basically, if we have a network, which is node, routers, hosts connected with links, some kind of different switches, different protocols, different types of links, you need some mechanisms to figure out what is the best path. So for example, if you want to reach from node G to node K, you need to know what exactly the path this packet is supposed to take. And one way to do it, kind of assign the kind of directions manually and semi-randomly, or you do something better, something smarter, and run some form of automatic discovery of the path, like in some way, and then install this path automatically on every node, so every node knows how to do the job. So basically, the algorithm that we're going to be talking in this part, or in this parts, a series of parts, is about figuring out the path, because you still need to figure some algorithm to calculate the path. And when we switch to the part of the routing protocols, then we're going to be talking how to apply this algorithm in actual settings. For the further discussion, we're going to be just using very simple notation of the graph, where there's N as a set of routers and E is a set of links. So basically, if we have A, B, C, D, E, F, so let's say this is A, B, C, D, E, F, so that would be the set of the routers, and the set of links is just AB, that's one part, AC, probably the other one, AD, BC, let me just finish drawing what I have here, BC, C. Anyhow, I hope you got the kind of the basic idea what is happening. And one additional notation is a cost of path. So in one, you can have a cost of individual link. So basically, if you have a JSON link between A and B, that would be similar, simply weight of that link. And for the additionally, you can have a cost of a specific path, where you have kind of basically enumerating specific links that you're going through, and kind of sum of individual weights will be the cost of this specific path. So that's very, very basic notation but will be quite useful for further calculations. There are two major categories of routing algorithms that can be roughly split into the link state and distance vector. With the link state, one specific distinction is each router independently computes the routes to all other destinations given the topology. So you have like somehow there is a mechanism, and that's what would be the mechanism for the routing protocols, to discover what is the topology, and link state protocol, given the topology, simply do a few calculations. It's still complex calculations, but you do calculations and figure out what to do. Distance vector is quite different algorithm. You can actually classify it more like distributed algorithm, where each router requires some form of iterative process with the communication with its neighbors. So there's an initial iteration, it's kind of doing some initial calculations. At the iteration 2, it obtains information from the neighbors, recalculates, again, obtain information to the neighbors and share information to the neighbors, recalculates, and recalculates. And eventually it gets to the kind of basically the same state. So the output in both algorithms will be the same. It's just different inputs at different points of time. So there is for the link state, the input is the topology. Input for distance vector is vectors or distance vectors from neighbors, and sharing of those distance vectors to neighbors that you have calculated. That's the idea. So for the link state algorithm, there is nothing too special. It's just there is a notion of graph or knowledge of the graph at each node, and at each node the node calculates the shortest path to all other destinations. What I try to highlight on this figure is the fact that different nodes have different understanding of what the shortest path is. For example, if we're looking at the node A, the shortest path will be represented by this tree. So basically, if you want to go to D, you have to go to C. However, from the perspective of node C, the picture is quite different, and picture is even more different from the perspective of completed node E. Both of them correct, like all of them correct. In addition to the link cost that we already defined is the CXY, we can also define DV, which is basically the kind of current value from the perspective of the node that is doing the calculation. What is the distance in whatever terms, or like what is the cost to reach that destination? For the guys to whom you directly connected, so that initial DV will be effectively the link cost. And this is what, because you know that you can reach the node A using cost 2, that would be DV to node A would be 2. So that's basically it. And there's another special initialization is all other nodes that you cannot reach directly will be initialized to the so-called infinity. Another special notation is this PV, which means the node right before V along the best path. This one is not exact, so this will be needed to calculate the next hop. So given some other destination from my perspective is multiple hops away and I have 15 neighbors, and I will need to figure out which neighbor I need to go to. So PV will be needed to calculate this next hop, but by itself it's actually on the opposite side. So if you if I can reach V, so what would be the previous node to reach V? So it's basically kind of a reverse reverse path to the destination. And prime is basically the set of the nodes that you already found the shortest path. So the one that we already considered and the one that we still need to calculate the shortest path. So let's kind of get to the algorithm, and we'll try to do a small exercise and to try to understand this algorithm. So first of all, this is link state algorithm, and there are a few tutorials that you can look up online that maybe with some additional animations, and even Wikipedia potentially have a bit of animations. But the algorithm is by itself is quite simple. If you already taken algorithm class, it would be even simpler for you because that's one of the fundamental algorithms in there. But even though if you didn't take that one, it still be simple. It's kind of nothing special. So basically, the first part that is shown here is that initialization. So like you initialize this DV for all neighbors that you have, you initialize this to the actual ways to that link, and for everything else you initialize to infinity. And just to kind of consider here, we're calculating from the perspective of node A here. And because we are node A, we don't really care that whatever shortest path from the perspective of F. If I was F node, then the calculations would be slightly different. I mean, the order of will be different, but the calculations will be the same. And in another initialization is kind of n prime, where we initializing this set of nodes that we already considered. We put ourselves because we know we cannot reach. We already reached ourselves. This is our basically that's it. And the rest is quite simple. So what we do, we trying to find a node in universe of nodes that we have not yet considered, such that the distance to that node from whatever distance this that we already initialized and we'll update a little bit later is minimal. So from the initial perspective, we're gonna have dv initialized for node D, node B, and node C. And this D for node C would be exactly 5. So basically this number for node C, for node D will be 1 based on this one, and for node B for this one, so it's a DB, it will be initialized to 2. And among all this, and the rest will be infinity, and we don't have any more nodes available. So that's it. So what we do next is we simply pick the smallest among all these values, and the smallest one is 1. So we pick node D for the further consideration. We extend the n prime to include the node D. So now our n prime contains A and D. And we're trying to update all the weights, like all the D, for all neighbors of the node. So basically all neighbors of D that not yet been considered. So for example, if A we already considered, so we're not going to be looking at, but we're going to look at the weights for B, C, and E, because these have connections in there. And what the evaluations, what kind of consideration there is whether we can reach that node, being kind of a neighbor considered, either through that node or by whatever other means necessary that is possible to reach that node. So for example, we can consider E, and what we're seeing that E can be reached through D, so basically the weight of 1 plus additional 1. And this 1 plus 1 is probably less than infinity, so at that point we actually define that D of E is now 2. That's basic kind of mathematics. Then we're looking at the C. From the perspective of C, we now can reach the C has been initialized to 5 because we have a link to direct link from A with the weight of 5. But we still can reach C through node D. So in this case, we have A, D already been initialized to 1 plus distance from D to C, which is 3, which is kind of you can calculate to 4, and 4 happened to be less than 5. So at this point, DC is what is this? 4, and don't forget that we also need to update this PV. So PC now is D, and initially it was set to P C was initialized to A, and this is for infinity we don't have anyways, and for this one is PED is directly to A, and this one is also the same, initialized to A. So that's kind of basic process. And we're done with this step, and we just go into the next iteration of this process. Now we have less nodes to consider, so we now have C, B, E, and F to look at, and we're just looking for the smallest one. And I think among the smallest ones we have node E with 2, we node have a B with 2, and there's something with 4, and something with infinity. So now we have this 2 nodes basically with the same weight, and technically from the perspective of algorithm, to correctness of the algorithm, it doesn't matter which one we pick because in both cases it will be correct. From the protocol perspective, you always have some break criteria to break the tie. For example, and kind of if I present any questions on the exam about that, then there's will be just specified. So for example, if there's a tie, you pick the node with the smallest lexicographical, kind of in lexicographical order. So in this case, you pick node B. The only node that needs to be considered at this point of time is node C. And we just need to evaluate whether node C, kind of the current weight of node C4 is less or more than weight would be if you reach node C through B. And in this case, it's a weight of 2 plus 3, which is 5, and that happens to be larger than 4, and we're just not considering, and basically in this process, everything stops. And we go back iteration, and now considering node E, and what we're going to be considering is node C, node F. And actually the interesting part that at this point we'll be actually changing again how we can reach node C. So in this case it will be node E currently 2 plus this weight of 1, which is 3, and this is how we can reach node C at this point. So what we be updating is node C equal 3, and P of C is now E, because this is the previous node that from that destination. And when we consider node F, we simply, there's infinity is more than anything else. So in this case, it will be D of F equal 2 plus 2, which is 4. And P of F will be basically the same E. And I think I think we have calculated all of them, like considered all the nodes. Let me double check. Yeah, I think we considered all of them. So that would be basically the vector of the vector d and vector p will effectively define what is the value for the shortest path, and from the kind of p you can actually infer what the actual path is. And you need to do a little bit of mathematics, or a little bit backtracking to actually figure out what is the next hop for each of the paths. And if you're interested, you can play a little bit of kind of logic with these examples on the slides at home, but it's exactly the same as what I'm just covering it. So we considered node A, we recalculated D and recalculated P, we picked node D, this is the same one, then we picked node A, we pick node E, we can pick node B, C, F, and look at it. Each step we basically recalculated paths, and now we can end up calculating the actual destinations. So to kind of highlight how you can calculate the next hops. So let's say we want to calculate the next hop for node F. This is because it's the farthest one, but logically what you're going to do, you enumerate all the nodes and try to do the backtracking and calculation of the next hop for each of them. But just consider it node F. So what you're going to do is consider what is P of F. So P of F is, in this example, is E. So that would be previous hop. Then you consider what is P of E. In this case, it's supposed to be D. And P of D is, I think it should be A. So as soon as it's A, that means that the F can be reached if A forwards to D. So basically, this is the kind of stopping condition, and you need to be considered this as a next hop. And I hope you can get the idea that you can easily calculate everything for each hop. You can calculate for each destination. You can figure out what is the next hop to the destination. So that's basically it. Depending on which specific data structures are being used and kind of specific optimizations defined in the implementation, it can be implemented either of n square, which is not exactly ideal, or even much better with n log n. But note that this is a complexity from perspective of individual router, and overall complexity is still larger because each router calculates on its own. So you can basically multiply by the number of routers if you want to consider overall complexity of the algorithm. It's not really that important because always it's kind of from perspective of the same router. But just remember, we're still talking about the whole system, and the whole system is quite big. One additional consideration is about the link cost. This is not exactly a conversation of the algorithm because algorithm is just abstract concept, but what you need to know is the cost kind of even it's tempted to be associated with the amount of traffic carried in the network. So kind of to use it for the purpose of some form of load balancing, it can be a little bit dangerous. And dangerous in terms of you can calculate the route and traffic switches in one direction, which triggers the kind of change in links, and kind of you have to recalculate again, you switch the traffic, you recalculate again and switch the traffic and so forth. So in simple terms, you have to have a reasonably stable weights that don't depend on the kind of actual result of your calculations, and people usually don't do this kind of not too smart things. But in any case, what I want you to remember about the link state protocol, that it requires knowledge of the complete topology, and the whole calculations, it can be done by individual node within number of steps, but it's just as fast as it can just simply do these calculations and be done. Okay, so I hope you got the idea of the link state protocol. Remember the Dijkstra, try to practice a little bit the Dijkstra algorithm on simple topologies. Again, not saying anything about exams in here. But in any case, hope it was interesting, and we'll see next in the next module about the distance vector protocol.